So I tried to make this lecture a little bit shorter, and this quiz is a little bit shorter. It's only 3 questions this time, but I do have a couple slides just to cover of some important material related to groundwater. So what you finished up with on the prior quiz was that you were trying to think about what would happen in situations where you're either adding water to the ground. Does that make water table drop or fall? Drop or rise. And then if you're taking water out of the ground, what does that do to an aquifer? So just to remind you the definitions, if you have discharge, you're taking water out of an aquifer, usually through a well, pumping water out of the ground. Recharge is you're adding water to an aquifer. So a good situation is when recharge is greater than discharge. So if you're adding more to an aquifer than you're taking out, this is called groundwater replenishment. And that's a good thing. So the water table will rise in that situation because you're adding more water to the ground than you're taking out of the ground. The opposite, if you have more discharge than recharge, so you're taking more water out of the ground than you're putting into the ground, we call that groundwater depletion. It's also called over-extraction or groundwater mining. Some geologists, including myself, would refer to groundwater as a non-renewable resource. And the reason for that is because in many places around the globe, we're taking too much water out of the ground than is naturally being replenished. So we're actually mining water and we're taking it out of the ground almost as if it's a fossil fuel. So if you don't know how a well works, I just wanted to kind of show you the general mechanics of a well. This is kind of my area of specialty, so I teach an entire course on groundwater and surface water here at the university, but basically you might have seen one of these old hand pump wells. So if you take the handle and you push it up and down, you can basically build suction and you can draw water out of the ground. Another example of this would be the same as if you were using a straw and then you apply suction and you pull water out of your drink with the straw. A well works the same way. So by adding a little bit of pressure and adding a little bit of suction, you can draw water out of the ground, fill up a container. So that's kind of old-fashioned wells. The modern ones are going to have electric pumps, so it will have an electric line hooked up to it. So that's this pipe here on the side. And then inside of this pipe, there's going to be an electric pump that's working the same way as the handle pump in the image on the top. So this is a groundwater well for irrigation. Usually each well like this can cost about $100,000 to upwards of $1 million for farmers when they install this type of well. A standard household well in Massachusetts costs about $15,000 to install. So if you ever run out of water at your house and you have to drill your well deeper, it'll cost you $10,000 to upwards of $20,000 with an average of about $15,000. So if you have a household basically has a electric well. So you dig a hole and then you put an electric pump into that hole. That will pump water up to the surface down into your basement. And then you'll have a storage tank and that'll distribute it around the pipes in your house. So just to show you, if you have a well and you are actively pumping it like this, these people here pumping this well, if you are actively pumping a well, a feature will form that's called a cone of depression. So if you're taking water out of the ground, there's a feature that will form that I've outlined in red here. It's called a cone of depression. So normally this water table here should go straight across all the way, the dashed line here. It should go straight across all the way, but as soon as you start taking water out of the ground, you form this feature that's called a cone of depression. So these are usually okay until if you kept pumping this aquifer and this cone of depression went all the way down below this well, then your well goes dry and you run out of water as a homeowner. So you can't cook, can't clean, can't shower, have no drinking water. So that's called a cone of depression. And if you have multiple houses that are in close proximity to each other and they all have their own wells and they are all creating their own cones of depression by taking water out of the ground, what can happen is that they can overlap. So if you have house 1, house 2, house 3, and house 4, and all of those are basically suctioning water out of the ground with a straw, a well, what can happen is that it's a little bit hard to see, but there's a horizontal dashed line right here. That's the original water table. By taking water out of the ground, you produce this cone of depression. And what has happened to house number 3 here is that the water table has dropped below the bottom of their well. So their well has gone dry. So this is the issue with taking too much water out of the ground, and a consequence of human activity is that you can cause people to lose their water supply. And then what do? What do you do if you don't have water in your house? Okay. Another example of something caused by human activities is land subsidence. So, land subsidence is basically the idea that if you have a flat land surface and you start taking water out of the ground underneath of it, the land is going to sink. So, it will form kind of this bowl shaped depression that where it used to be flat land, it has now subsided and it has now sink down. So, the reason to this is that if you're taking water out of the ground where it used to be full of water, the pores that the water would be stored in have now shrunk, and then the ground will collapse basically on itself, form kind of like a sinkhole, or you can get cracks in the ground due to this land subsidence. So this picture is from California. This was not created by a fault. This was not created by an earthquake. This was created by taking too much water out of the ground. So a good analogy for this is that if you have a sponge, it's wet, you leave it to dry on the sink, you should realize basically that as it dries out, it shrinks down. The ground will do the same thing. The ground is like a giant sponge. If you dry out the ground will shrink. And that is what we call land subsidence. If you want a video explaining with some more visuals of what I just said, there is a link to it right here on the slide. So let's talk about an area that is going through this environmental issue of land subsidence. You're also going to read a case study about this for your groundwater homework. This is the Central Valley of California. So if we're looking at the entire state of California here, we're just looking at this zone right here, kind of to the east of San Francisco, and then it goes south as well. So that's called the Central Valley of California. That is an area that has instances of subsidence, land sinking down. So the blue color in the map here indicates to you an area of major subsidence based on our key up here. So blue area, major subsidence. Just to give you an analogy, so this is a telephone pole or a power pole, and in 1925, this is where the ground surface was, and then that ground surface, due to taking too much water out of the ground, dropped by this much in that 30 years, and then basically another 22 years passed, and in that entire time, the ground had sank 9 meters, so that's about 30, if you want to just estimate a little bit, that's about 30 feet. So the ground was 30 feet higher 50 years prior. But by taking water out of the ground sank and sank and sank and sank. There's still one more issue that's a consequence of human activities, and that's saltwater intrusion. So Cape Cod has major issues with this problem. And what can happen is that if you have a coastal area that is using fresh water from underground as their drinking water supply, if they happen to take too much water out of the ground, what they'll do is they'll cause the ocean to intrude and go inland. And then now, instead of taking fresh water out of the ground, you are taking ocean water into your well. So you can't obviously drink salt water. You can't take ocean water. It's going to corrode your pipes. It's going to rust the pipes. So it's something that has to be taken care of or careful with. If you're too close to the ocean and you overpump water out of the ground, you cause the ocean to intrude and you get salt water out of your faucets. All right, so let me show you an example, an animation of that. All right. So we have this coastal area, and the lighter blue color indicates freshwater. So that's freshwater. The green indicates saltwater, and then we have this well, which will start pumping in a second. So the highlight is just showing us the zone between freshwater and saltwater. And then if you have a well in that coastal area and it starts to pump water out of the ground, if they take too much out of the ground, you'll notice that the salt water starts to shift inland. And then eventually it's going to intersect that well. It will get sucked up into that well. And then that well is contaminated and can no longer be used because you've now corroded it with salt water. So where is this issue happening? Groundwater overextraction. This is a map of the entire US. Anything that's in red or orange or kind of the yellowish color, that's an area where groundwater overextraction is happening. It's the most severe in the center of the US. So this is the Ogallala or High Plains Aquifer here, number 13. That has a major issue with groundwater overextraction. This is the Central Valley, number 14 over here, major issue with over-extraction. We have issues in the Mississippi River Valley as well with groundwater over-extraction. So the more red the color, the worse the situation is in the US in terms of this issue. Just to finish up, I want to make one final note about groundwater pollution. So it's very easy for groundwater to become contaminated. It's very easy for it to become polluted because anything that we spill on Earth's surface can just soak into the ground and then get into groundwater. So if we look at it, it's very easy to contaminate, but it's very difficult to clean up. So once something like a factory has some kind of leak and that stuff, those chemicals go into groundwater, it's expensive to clean up because you're going to have to dig a giant hole in the ground to try to intersect this water and this contamination. So it's difficult in that sense. It's also expensive because you got to spend a lot of money to try to fix a problem that you can't see because it's underground, buried under 100, 200 feet of rock or soil. So it's better to just prevent pollution in the first place because it's so expensive and difficult to clean up. If you have a contamination event, it produces something called a plume. So a plume is basically like this kind of circular area. Basically, you have a central leak right here, and then that plume will kind of move and spread out away from the original leak or the original source. So the point of this figure here is just to show you once groundwater is contaminated, it doesn't stay put, it tends to move, which makes it even more difficult to try to clean up. So when we're looking at contamination, we can put it into one of two categories. It's either what we call point source pollution, which means you know exactly where it's coming from. That could be something like a factory or a power plant or a wastewater treatment plant, a landfill. Those are point sources, so you know exactly where pollution is coming from. There's also another source of groundwater pollution, and that's called a non-point source. What that means is that you don't know where it's coming from. So it's from a wide area. You can't pinpoint it, point your finger at it and say, I know this pollution comes from right here. So it tends to be from wider areas. So examples are agriculture. Examples are septic tanks from houses that leak over time, or neighborhoods as well. Excuse me. I didn't pause it because I only have one slide left. So here's your final slide. And you're looking at common pollutants in drinking water. So I have just an example list here of different types of things that get into drinking water and then the issues that they might cause. So benzene is an example, trichloroethane, arsenic, nitrate, lead, cryptosporidium, and something called PFAS. So your final quiz question is that you're going to pick two of these pollutants. What are they? How do they get into water? What are the sources of those in water? What are the health effects? And then does this concern you? So you're going to have to do a little bit of your own kind of research and work to look at two of these examples from the list that I've given you.